Okay, chapter 4 is about pricing options, and this is a fun chapter for me because it's not about science or engineering applications, it's about financial applications. And so what is an option? Well, if someone writes on a piece of paper, I promise to sell you such and such for price E at some future time T, if you want to buy it then, how much is that piece of paper worth? That's the question. If the asset, which might be a stock, but it might be a barrel of oil or a bushel of wheat or most anything, he's promising to sell it to you for a certain price in some future time if you want to buy it. It's optional. You don't have to buy it if you don't want to. The question is, how much is that worth? Well, let's say that asset, that stock or whatever, is worth a little less now at time T, which is now, and at time capital T, he promises to sell it to you for a price E. Then if you knew how much that thing was going to be worth on the open market at that future time, then it'd be easy to figure out how much the option is worth, because if the price of the asset is bigger than E, then the option is worth S minus E, because you're either saving that much by, if you're going to keep it, or you can go sell it on the open market and actually make that much profit. But either way, it's worth capital S minus E if you knew capital S, if you knew the future price. And if it's worth less than E, then it's the option. You just won't buy it. You wouldn't be stupid enough to pay more than the open market price, so you just won't exercise your option. So the value of that option, that piece of paper, is the maximum of 0 and S minus E if the future price is capital S. Well, you don't know the future price, so what if you could come up with a probability distribution, though, a reasonable probability distribution for the future price, Q of S? Then you could calculate a reasonable value for the option as the integral of the value if the future price is S times the probability that the future price will be S. And that would give you a reasonable value for that option. At least that would be the value of the option at the future time. But if the inflation rate is R, little r, then you need to adjust that down by this amount, because what you really want to know is how much is that piece of paper worth now, not how much is it worth a year or 5 from now, but how much is it worth now. So you take the value of the option at that future time and knock it down by the inflation rate. So the basic question is, can we come up with a reasonable probability distribution for the future price of an asset that's worth a little less now at future time T? Then we could figure out a reasonable value, how much you should pay for that option. Now, before we go on, you might say this is a game for speculators that want to get rich quick, but really it's more of insurance for people that don't want to get poor quick. For example, typically somebody's building a manufacturing plant, and it's going to take them 5 years to build it, and they know that in 5 years they're going to need to purchase a certain amount of equipment. They don't want to purchase it now because it'd just be sitting around for 5 years, but they don't want to take a chance that equipment might rise 1,000%. So they buy an option and say, well, you're committing to selling it to me for this price in 5 years, and that way I can be sure that I don't end up paying more than I can afford. So it's more of an insurance policy than gambling. And the question is, how much should the guy pay for that option? How much is it worth? And again, if we knew the future value of the stuff he wants to buy, then it would be easy. If we have a reasonable probability distribution for the future price, then we can figure out the expected value. So the question boils down to, what is a reasonable reasonable probability distribution for the future price of that asset? And of course, we're assuming we don't have any insider trader information. If we knew some secret information, we could do a lot better than this, but we're assuming that we don't know anything basically just depending on luck for the distribution. So assuming you don't know anything specific about that asset, the future price, what's going to happen in the future, what's a reasonable probability distribution? Well, the first thing you might say would be, the reasonable thing would be a normal distribution around S. In other words, if the price of that asset is little s now, then the future time the price distribution would probably be a normal distribution with mean of little s, and the variance is going to increase with time, clearly. But if you think about that a second, that's not completely reasonable, because just a normal distribution, the tail would actually not go to zero until minus infinity, which means that there's going to be some probability of a negative price, which is impossible. And it's really not, that's a normal distribution of the price is not really reasonable. A log normal is more reasonable, because say each time step the price is not going to go up or down by a certain amount. It's going to go up or down by a certain factor, is a more reasonable assumption. So we're going to assume that say every dt time steps you flip a coin and it either goes up by a factor of r or down by a factor of r, not up by an amount r or down by amount r. Then it would be a normal distribution, but it'd be a log normal if it goes up, if there's equal probability that it goes up by a factor of r or down by a factor of r. That means that the log of the price is going to have a normal distribution, because the log goes up or down by the same amount depending on how you flip the coin. So we're going to flip a bunch of coins, and the price is either going to go up by a factor of r if it's heads, and goes down by a factor of r if it's tails. And it's actually going to be a binomial distribution, but if you do that with a small enough dt, you do it, continuously essentially, then that binomial distribution is approximated by a normal distribution, is well known. And in fact, so that means that the log of the future price should have a normal distribution. So that's going to be our assumption. So the log of that price, capital S, is going to have a normal distribution with variance sigma squared, and where sigma squared is going to be, if we take the example where you're flipping a coin every dt time steps, and it goes up or down by a factor of r, then you can show that the variance of that future distribution is going to be proportional to the time, t minus t, capital, the amount of time that passes from now until when you exercise the option. And then there's going to be the sigma 1 is called the volatility. That depends on the stock, of course, if or whatever the stock or the asset. If it's very volatile, that means it changes rapidly. That would be the factor that you're multiplying or dividing by is large, and you do it very often. So that depends on the asset itself. The volatility, it's basically the variance after 1 year. See, if capital T minus T is 1, then sigma 1 is the same as sigma. So you can think of the volatility as being the variance after 1 year. But then after 2 years, the variance would be twice as big, and so forth. The standard deviation would be square root of 2. So basically the standard deviation is proportional to the square root of the time that passes. The variance is proportional to the time that passes, and that's a reasonable distribution. Again, if you flip a coin every dt time steps and it goes up or down by a factor of r, then you can show that it's going to be a binomial distribution. It will be very closely the log of s will be a binomial distribution, which is very closely approximated by a normal distribution, with this variance where the sigma 1 basically has a dt in the denominator and an r in the numerator. The bigger r is, and the bigger the volatility is, and the smaller dt is, the bigger the volatility is. But it's proportional to the time that passes, basically. That's the important thing. Okay, well, what about this alpha? Well, it seems like alpha should be the log of little s. It seems like the peak, this log normal distribution is going to have a peak at where log of s is equal to alpha. In other words, where s is equal to e to the alpha. And you might say at first glance that it should have a peak at capital S equals little s. If little s is the original price at time t, then this log normal distribution, you would think it would have a peak at little s here and be a log normal distribution with a peak there. But first place, you don't really want the peak to be little s. You got to account for inflation, so you'd like for the peak to be s times the amount of inflation that's gone by. So by that reasoning, the peak in your future price expectation probability function should be s times e to the r t minus t. So this, forget this last term here, ignore that. That would seem to be reasonable for the peak of the log normal distribution, that it should be s, but s adjusted up for inflation. But what is this other term here? So alpha is actually this, which means that the peak occurs here, and that part seems reasonable. That's the original price. You adjust it for inflation, you'd expect that the peak would be that. But we're multiplying by another factor here. Well, the other factor is in there so that the mean, not the peak, is what you'd expect it to be. In other words, for a normal distribution, the peak and the mean are the same, but for a log normal, the mean is higher than the peak, which isn't hard to understand. So you have to adjust it down, just the peak down, so because you don't really want the peak of that distribution to be s times inflation rate, you want the mean to be s times the inflation rate. At least that seems more reasonable. So anyway, that's the probability distribution we're going to use. It's a log normal distribution with variance which increases with time, which makes sense. The further in the future you try to predict the price, the less accurate you're going to be. And it depends on the volatility, which is the inherent variance of the stock or whatever. If it's something that traditionally varies very rapidly, then the sigma 1, the volatility to be large. If it's something whose price has been stable over the ages, then it's going to be small variance. So now we are able to calculate the value of that option, and this is what it's worth. It's the expected value of your profit, assuming a log normal probability distribution, and it's reasonable, but with finance is not nearly as exact as science or engineering. That's assuming some things that are hard to justify. So we can calculate a reasonable value without knowing anything specific about the future price, just assuming blind luck that the price is going to go up or down by a certain factor every certain time, which depends on the volatility and, of course, the amount of time that passes. That's going to spread out more. But that's a call option. Now, there's also something called a put option, which is a little piece of paper that says, I promise to buy this asset from you at price E at future time T if you want to sell it then. And again, this is kind of an insurance policy. A farmer is going to have a crop of corn in a year from now, and he doesn't want to gamble with the price. The price might fall, might bottom out, and he'd go broke. So he wants to guarantee that he won't go broke, and he's willing to pay a certain amount insurance premium for that. So he finds somebody that says, well, no matter what happens to the price of corn over the next year, I'll promise to buy it from you at this price per bushel at this time if you want to sell it then. So that's a put option. And again, if you knew what the price of that corn was going to be a year from now, you could figure out exactly how much that put option was worth. It would be E minus S, because he's going to buy it from you at E, and if it's only worth capital S, then you've made a profit of E minus S, whether you keep it or, well, so, but again, you don't know the future price, so we assume a probability distribution. We can use that same probability distribution, that Q of S, exactly the same Q of S before. We assume that the current price of the whatever it is you want to sell is little s, and the future price is distributed with a probability distribution in a log normal, where the mean of this log normal is going to be little s adjusted for inflation. The peak is going to be smaller than the mean, but we're really interested in the mean. So we assume a log normal distribution where the mean is little s adjusted for inflation. So you know, if he promises, if for example capital E is less than S, you might, little s, the current price, you might say, well, why would I agree to, you know, this option is worth nothing because he's promising to buy it from me at something that's less than the current price. Why would I do that? Well, because the current price might be even less than what he's offering in the future, so you're guaranteed that you can at least get E, so it's worth something. And the value is, again, you know, this is the value of the put option. It's either E minus S or 0 if S is bigger than E, and you multiply it by the probability distribution, which is exactly the same as for the put option, and that gives you a reasonable expected value of that option at the future time t, but then you adjust back for inflation, and that gives you the current value of that option. So that's how much you could reasonably be expected to pay for this little piece of paper. Notice that for a call option, the amount you pay for the option does not include the price you're supposed to pay for it. I mean, the price, the value of these options, that's the value of the little piece of paper with the promise on it. It doesn't include the price E that you have to actually pay to buy it for a call option. Okay, so we have derived the value of an asset. The value at current time t of an asset whose current price is little s is given by this, where capital P of S, that's the maximum of, well, if it's a call option, it's a maximum of 0 and S minus E. If it's a put option, it's a maximum of 0 and E minus S. That's what this is for both call and put option. And by the way, the 1 over S comes from the change of variables from log of S to S. But this is the probability, this is the log normal probability distribution. So basically this is the formula we've been talking about, the probability distribution times the maximum of 0 and S minus E or E minus S. That will give you the expected value of a piece of paper that says, I will buy or sell you this thing at time capital T for price E. So what's this got to do with partial differential equations? Well, that's a good question. You actually don't need to solve a partial differential equation then to figure out the value of that asset. You just integrate the probability distribution times the maximum of E 0 and S minus E, and that's it. But you can take this solution and derive a partial differential equation, which is what's done in this chapter. And here's the partial differential equation. It's called the Black-Scholes equation. Sigma 1 is the volatility that we talked about. S is the current price. Little r is the inflation rate. It's sometimes called the risk-free interest rate, but it's really inflation. It's how much the money is going up. And V is the value of that option. And it looks a lot like the heat equation here, Vt T plus something positive times VSS. It looks like the backwards heat equation. And we know we can't solve the backwards heat equation forward in time, but you can solve it backwards. And that's what you have to do because, what are the boundary conditions here? Well, you don't know V as a function of little s at little t. You know it at capital T, the final time. In other words, for a put option, the maximum of 0, E minus S, that is the exact value of that option at capital time T, capital T time, for a price, capital S. If you knew the exact price, if you knew the price at the final time, you could say exactly how much the value is. So that value of that option, you know exactly what it is at the final time. What you want to know is what's the value at the current time. So you solve the partial differential equation backwards in time, starting with initial conditions. For a put option, it would be V would be maximum of 0 and E minus S, or for call option, maximum of 0 and S minus E. So you can find the value at current time T by solving this backwards heat equation, the Black-Scholes equation, solving it backwards in time with initial values of, you know what the V as a function of S is at final time T, just that simple maximum of 0, E minus S or S minus E, and you solve it backwards to find what you really want. Now the obvious question is, though, why even bother solving a partial differential equation? We already got the solution. We just showed you with that integral you can calculate the value of the option at current time T just by integrating that integral. Well, one reason is this is a course on partial differential equations, so we have to have partial differential equations to solve. And another explanation is that if you solve this partial differential equation, you will know the value of the option not just at the current time and the current price, but at any time before capital T, whatever that price is. So for example, if you buy it now and you buy say a call option, somebody promises to sell you something in 5 years from now at a certain price, and you've paid for it, and 2 years from now the price has changed, and if you want to know, now how much is that option that I paid such and such for? Is it looking good, or can I sell it to somebody else now for, if so, how much? Well, anyway, if you solve the partial differential equation, you've got the value of that option for any time between now and the exercise time, capital T, for any price. So it's worth something. The derivation of the Black-Scholes equations in Chapter 4 are actually based on an article I published in the College Mathematics Journal in 2018. The Black-Scholes equation, that partial differential equation, is normally derived in a totally different way using stochastic calculus, which I never understood. Some of you actually do. But I wanted to derive it in a way that made sense to me, that on basic principles, just saying what's a reasonable probability distribution and what's the expected value of the option given that probability distribution and so forth. And I was able to derive the Black-Scholes equation kind of actually more directly, I would say. But in any case, so it's based on a published article. Okay, now let's solve the Black-Scholes differential equation, and using these parameters. So this means that current time is 0, the exercise time is 0.5. So somebody has promised in half a year from now, I will, let's see, this is a call option. So I will sell this thing to you in half a year from now for $40 if you want to buy it then. And the volatility is 0.2, which we usually don't really know the volatility, but let's pretend like we do. The inflation rate is 10%, compounded instantaneously. And we want to figure out how much that option is worth at current time t equals 0. Well, this is actually the solution. This is what we're going to get from PD2D. We started at t equals 1/2 and went backwards, solving Black-Scholes equations backwards in time. And this is the solution. And in particular, if the current price is $39, then PD2D calculates that the value of that option, if the current price is $39, is $2.68. Remember, he's promising to sell it to us for $40, so he's promising to sell it at more than it's worth now, and yet it's still worth $2 because there's a reasonable chance it's going to be worth more than $40, and so we can make a profit by buying it for $40 in half a year from now. So that's the value of the option now if the current price is $39. Remember, he's going to sell it to us for $40 in half a year. If the current price is $50, well, he probably wouldn't offer to sell it for $40, but if he did, then we're going to make a pretty good profit. But even if its current price is $39, we still make a little bit of profit, expected profit, because there's enough chance that it's higher than $40 that we can expect some profit. So the solution tells us how much it's worth for any current price at current time. But you don't actually have to solve a partial differential equation. You can just calculate that integral. In fact, we're going to do it both ways. But this is a course on partial differential equations, so let's solve the partial differential equation with E equals 40, R equals 0.1, volatility of 0.2. This S max, that's just, you can't solve it for S out to infinity. You got to stop somewhere and stop enough above the strike price 40 to where it won't affect what you choose for the maximum S, won't affect the value. Okay, let's solve this example. Example 1 in the book. Could use the GUI because we're going to use collocation, which is definitely better for this than the Galerkin method, because it's not so easy to put into divergence form, so collocation works much better in this chapter. So I could use the GUI, but I'm going to use the interactive driver anyway. Don't want to do an example. It's a 1D problem. It's time dependent. Black-Scholes equation is time dependent, but one space variable, actually the variable is S, the current price. We're going to have to call that X. The PD2D allows you to give any names you want to the unknowns, but the variables have to be T and X and Y and Z. So we're going to have to replace S by X. So it's 1D problem, one space variable, namely S, actually price. And we need to use collocation. Double precision always. R is the inflation rate, 0.1. The volatility was 0.2. The strike price was 40. Maximum price that we're going to look at, since current value is 39 and he's offering to sell it to us at the current price of the asset is 39, and the strike price, the amount that he's willing to sell it, is 40, so 100 ought to be enough above that there's no chance it's going to be worth more than $100. And I believe that's all the parameters we need. Grid, well, let's do 101 grid points from 0 out to 100 S max. I could make them non-uniform, but I don't want to bother with that right now. This allows you to make a non-uniform grid, but by default it's going to be uniform from 0 to S max, which is 100. And it's time dependent. Okay, now we want to go, notice that it says TF is not required to be greater than T0. Usually we go forward in time. Now the initial time is going to be 0.5 and the final time is going to be 0. So we're actually solving it backwards. We have to. The initial conditions are given. We know the value of the asset at the 6 months from now. We don't know its value now. That's what we're trying to find. So we can go backwards, not a problem. Is it linear? Yes. Want the time step to be chosen adaptively? Yeah, why not? Okay, there's only one partial differential equation. We want to call the unknown v because we've called it v. And no, I don't need any intervals. Okay, partial differential equation is C, which is just 1 times dv dt is equal to minus 1/2 times sigma 1 squared times s squared, but remember s has to be, is x. PD2D requires the space variable in a 1D problem to be called x. So that's volatility squared times s squared, we got to write s as x, times v, vxx, minus r times s, which we have to call x, times vx, vs, which we have to call vx, plus r times v. Okay, there's the differential equation. Now the initial condition of that means at t0, which is 0.5, the value is the maximum of 0 and s minus e, which we have to call x. No periodic boundary conditions. Now the boundary conditions, okay, we didn't talk about that, but at s equals 0 and s equal to s max, we need to have boundary conditions. It's a second order equation. So the boundary condition at s equals 0 is just v equals 0, because if the price is 0, it's going to stay 0 and the option is worthless. It'll never be worth more than $40, so you can't make any profit. So if it starts exactly 0, it's going to go up or down by a factor of r. It means it's going to stay 0 forever. Now at the other end, well, the boundary condition is going to be v sub s equal to 1. I'll have to explain that later when we look at the graph there. That's not quite as obvious. We'll look at the graph and I'll explain why that boundary condition at, basically that's saying that for every dollar that the price increases, your expected value of the option increases by $1. I guess that's all you need to know. If the price is 0, then the value of the option, if the current price is 0, then the value of the option is going to be 0. If the current price, or at any future time, the price is ever real large, then what you can say is that for every dollar the price increases even more, the profit's going to increase by $1 because there's no chance it's going to get below E. See, if it starts out at 0, there's no chance it's going to get above E, so it's going to be worthless. If it starts way above E, there's no chance it's going to ever be less than E. So if you go from $100 to $101, you're going to make $1 profit more, so the value of the option goes up by $1. Okay, I just want to plot the value as function of x, value of v. Okay, we're done. Now let's see if it works. If it doesn't, that's fine. We'll make it work. Okay, well, we actually got a compile error there, and that was because I said the maximum of 0, s minus e, and s minus e is double precision and 0 is an integer, and it didn't like the mixing integer. And so anyway, I fixed that. I just changed the 0 to 0.d0, and now it works. Let's run it again and look at the output. Okay, here, this is the value of the option as a function of x, which is price, at the final time, and it's just, you know, if the price is $40, the option's worth 0. Then if it's $50, it's worth $10. If it's worth $30, it's worth 0, and so forth. That was our initial conditions. Now, if we go backwards in time, that's at 4/10 of a year, 3/10 of a year, 2/10, 0/10. That's essentially 0. So this is the final time t. That's the current time t equals 0, and you see the that's now the value. So if the current price is 39, you go up here and well, I printed out the result. It's actually close to the $2.68. You can't tell from this graph, but you can print out the result, and it's all reasonable. So basically, if the current price is $20 and he's offering to sell it to us for $40 in half a year, then that option is almost completely worthless, but not quite. Its value is extremely small because it's very unlikely that it's going to be worth more than $40 in half a year. Okay, the book, we calculate the value of that option another way. Remember that the current price of the asset is $39. He's promising to buy it at $40 in half a year from now. And you really don't need to solve a partial differential equation, just to evaluate that integral, which is what we do here, and print it out, and it's again 2.68 agrees with the partial differential equation solution. And there's a third way that this can be done. You can get that same, you can figure out the value of the option if the current price is 39 and he's offering to sell it to you for $40 in half a year. Again, it's worth something because even though he's offering to sell it for more than the current price, the price might go up above $40, in which case you can still make a profit. So the third way of doing that is a Monte Carlo simulation, and a program for that is shown in the book also. And basically you just actually start out at $39 and flip a coin every dt time steps. You flip a coin with a random number generator. If it's heads, greater than 0.5, you go up. The price goes up by a factor of r. If it's tails, it goes down by a factor of r. You just do that until you get to half a year from now, and then you say, okay, now how much was the option worth? Well, it's going to be whatever the final price is minus e, 0, the maximum of those, and then you have to adjust it down for inflation. Then you just simply do that millions of times and take an average. So you're kind of doing a direct experiment, and that also comes out with the same value. And your homework problem number 2 is a put option, where you're going to do all 3 ways of calculating the value of that put option by actually solving the partial differential equation using PD2D, by calculating the integral, and by doing the Monte Carlo simulation. And you can basically use my Fortran program for the integral and adjust it appropriately, and you can take my Monte Carlo simulation and adjust it appropriately. And then the main part A is solve the partial differential equation using PD2D. So you should get the same value for the option. This is referring back to problem 1. Problem 1 was a call option where the current value of the asset is $25. He promises to sell it to us for $30 after 1 year. There's the interest rate volatility, and you're supposed to calculate the value of that put option 3 different ways, and you should get about the same value each time.